Okay. Hello, all. So this is the lecture for Chapter 11, which is Artificial Intelligence. And just so everyone knows, there's only one more lecture left, and then class is over. So let's go ahead and get moving on it. So in Chapter 11, we are going to go through all the different sections 1 through 7. We're going to talk about artificial intelligence, what it means, what it doesn't mean. We're going to go into robotics. Now, one thing I am going to say is that I took out a lot of the coding aspects of this chapter. If you would like to see the code in action, definitely make sure you read those sections in the book. So we're just going to kind of talk about more of the concepts and the things that go on when we're talking about artificial intelligence. So intelligent machines. So we talk about intelligent machines and we say that there is an agent, and this agent is a device that is going to respond to stimuli from its environment. So it can be done in many different ways. It can be done through sensors or actuators, and much of the understanding and research in artificial intelligence is viewed at how to build these different agents to behave more intelligently. In the end, the whole object of artificial intelligence is to make a computer think as much like a human as possible. So we usually try and find various agents in order to do that. Now, different levels of intelligent behavior. There is very many different levels. One of them is a reflex. So that is a cause and effect type thing where it is an action is predetermined based on a previous action or an input. So, you know, it's kind of like if this happens, then this. Now, more intelligent behaviors, though, are going to require that the environment is going to have things such as goal seeking and learning. And we'll go into what both of those mean within context here in the next few slides. So moving forward, we are going to introduce an agent that is designed to solve one of these little mini puzzles. I used to get them as a kid. Maybe I'm just showing my age, sorry. But the numbers are traditionally all jumbled up and you have to move them in order. So typically it is a square tile labeled 1 through 8 with one blank space that allows you to slide the tiles around. So you can slide a tile into the open spot and arrange the numbers, and the goal is that it looks just like it does up in this graphic where the numbers are in fact in order. Now, our agent is going to take the form of a box, like in this picture. And the box is going to have it on some kind of gripper, a video camera, and a finger with some kind of rubberized end so that it can move those tiles. So when the agent is first turned on, the gripper is going to begin to open and close, and that gripper is what's going to hold that puzzle. We're going to put into it a puzzle that is scrambled up, right? And the gripper is going to hold onto it. After some short amount of time, the machine is going to lower that rubberized finger and begins pushing those tiles around. And once the tiles are in their original positions, the machine releases the puzzle and turns itself off. Okay, so this is going to this type of machine shows a few different aspects of an agent. So first, it's going to have to perceive that it is going to need an image of what the puzzle currently looks like, okay? So it's going to need to take that image from the camera of the puzzle and do something with it. We're going to talk about images here in just a moment, and you'll kind of understand a little bit more about what that process is going to take. Second of all, is that it is going to have to develop some sort of plan in order to move those tiles around to get the required outcome of the 1, 2, 3, 4, 5, 6, 7, 8. So it has to plan on where to move the tiles and when. But first, before we get into those two topics, let's look at a few different research models when it comes to artificial intelligence. So different approaches to research in artificial intelligence. One is an engineering track and one is a theoretical track. Now, the engineering track is that the scientists are trying to get the machine to exhibit behavior that is considered intelligent behavior. Okay. Now, the theoretical track, on the other hand, is trying to develop an understanding of the human intelligence. Okay. So the engineering is more performance oriented, where it needs to perform like a human, and a theoretical is more simulation, to where it will mimic the environment and the computational understanding of a human being. One thing that was created early on is called a Turing test. This was proposed by Alan Turing in 1950s, and it has served as the benchmark for measuring progress in the field of artificial intelligence. Now, number one, the test setup. You have an human interrogator, and it's going to communicate with the test subject by typewriter. In this graphic, your human interrogator is actually C. So C is communicating with both A and B via typewriter. Now, the test itself is, can the human interrogator distinguish which is the computer versus which is the human? They don't know. So C is going to have output from both A and B, and based on that output, can C determine if A is a computer or if B is a computer? So this is kind of where the benchmark has been set for artificial intelligence. So now that we understand this, let's go back to those two agent attributes we talked about earlier with the imaging and the goal setting. Now, in order for artificial intelligence to respond in an intelligent way to any type of input, it would help if I move the slide. There we go, sorry. In order for artificial intelligence to respond intelligently to any type of input from its sensors or actuators, it has to be able to understand the input. Now, when you're talking about input with artificial intelligence, you're talking about things much greater than a text and a typewriter input. So it's the ability to understand images and languages and many different other areas. So let's start with the area of images. When you understand an image, there are a few different ways that you can do. There is template matching. In the case of our problem solving, our little numeric puzzle machine, possible interpretations are limited, right? Your numbers can only be in one of the 9 positions. So it is actually relatively limited. We can assume that what happens is always an image that's going to contain the digits of 1 through 8 and in some sort of well-organized pattern and a blank. The problem is merely to extract the arrangement of these digits and where they fall. So it's just going to take that image, look for those markers, and then be able to process. So in order to understand images, it's a 2-step process. You have image processing and you have image analysis. So image processing, that is going to be able to identify the characteristics, something specific to that image. So edge enhancement, region finding, smoothing out rough edges. Whereas image analysis is going to understand what the characters mean. Okay, so your processing is to identify characters and your analysis is understanding those characters. So let's look at language next. Language processing, there are several different levels of analysis. The first level is called a syntactic analysis, whose major part of that is parsing. Okay, so you're going to divide it up and understand piecewise. Another level is called semantic, and as opposed to the syntactic, I can get these words out. Syntactic, where it breaks up each word, the semantic identifies the semantic role of each of these words within a sentence. So it's going to look at identifying things such as the action, the agent of the action, and what the object is. So it's going to be looking for those specific things from your sentence. The third level is the contextual analysis. This level that the context of where the sentence lies within other sentences is brought to that understanding. So you can see syntactic is just the word in general, semantic is sort of the word and action interaction, and context is how it interacts with those around it. This image is actually, yeah, there we go. This image is showing something called a semantic net. This is essentially a large linked data structure, okay, with parsing out the different pieces of the sentences. The pointers are going to indicate the associations between those items. Here, for example, this is a semantic net for the very, very easy sentence of Mary hit John. So you can see here you've got different names, you've got persons, you've got people, you've got objects, and you have agents. Again, it's just breaking it up into smaller different pieces. Next, we can talk about reasoning. So once an agent can accept input and produce output, what happens in the middle needs to be done, right? And that is the reasoning. So two methods of reasoning that we're going to look at is a production system and a search tree. So remember, we just spoke about the input and we know how to do output. This is the kind of that intelligence in the middle that makes the decision on what to do. So first, production systems. So in a production system, it is basically finding these common characteristics and isolating them, okay? So there are going to be three main components in a production system. A collection of states. So each state is a situation that might occur in the application environment. The beginning is called the start or the initial state, and the end is the goal state or states, because you could have multiple endings in it, okay? So part two is a collection of productions, rules, or moves. So a production is an operation that can be performed in the application environment to move it from one state to another. So each production might be associated with different preconditions. That is, so conditions might exist that present in the environments before a production can be applied. So productions in our case are moving these tiles from one position to another and slotting them around. Each movement of the tile is a precondition that the vacancy must be next to the tile. Otherwise, that tile cannot be moved. Third, we have a control system. The control system is the logic that is going to solve the problem of moving from the start state to the goal state. At each step in this process, the control system is going to have to decide which of the productions and preconditions are there, what that means in terms of what my next move could be. So, for example, let's go back to our 8 little tile game. There would be several different tiles next to an opening, okay? So you could actually do one of several different actions. So that is going to be several different productions that you can do. The control system is going to be what decides which tile to move into that vacancy, comparing it to all the others. Now, an important concept that in development of a control system is of the problem space. That is going to be the collection of all the different states, productions, and preconditions in a production system. A problem of space is often looked at in the form of a state graph. Now, here the term graph refers to a structure rather than a directed graph, which is kind of what you see in math, okay? So in this, we're talking about a collection of nodes connecting by arrows of what you can do, what is your next step, what could possibly be your next step, and that's kind of what we're showing here in this picture. What you can also have is something that is going to be a search tree, and that is going to be a record of state transitions, and you're going to be able to parse it the way we did a tree before, like that hierarchical tree, except, you know, it will be different decisions based on what the decision prior to it is. So you can do a breadth breadth first search or a depth first search. And that just means you can either search horizontally or vertically when you're looking in that tree. Perhaps the less obvious example of a production system is the problem of drawing logical conclusions based on given facts. So the productions in this context are using the rules of logic called inference rules that allow new statements to be formed based on old ones. So as an example, here's a figure. This shows basically a portion of a state graph that might be traversed when the conclusion Socrates is mortal is drawn from the previous three statements of Socrates is a man, all men are humans, and all humans are mortal. Therefore, Socrates is a human. So that's kind of where this whole inference rules comes into play. Now here, for example, we have a search tree, and it is basically a recorded state of every single possibility of every single move within and every single decision within your system. So here we're going to use this jumbled version of our tiles in a few slides. But if this is my given starting state, and we know what the ending state is going to be with the 1, 2, 3, 4, 5, 6, 7, 8, we can look at this tree until we get down to something that says 1, 2, 3, 4, 5, 6, 7, 8, which in this example is right here, and that's the goal. So you can search either breadth first or depth first, which just means are you going side to side, or are you going to exhaust it up and down before you make another decision. So in this one, it looks like it's doing breadth first, so it is going across as you go down, and it is exhausting every single possibility until it finds the goal. As it is going through every single one of these examples, it is actually creating a stack of instructions, and it is keeping the instructions that it knows works, and it is discarding the instructions that it knows that do not work. So we had talked about a stack. Remember, a stack of books you put on the top and you take off from the top. So here we've got the very first move that was made was actually the one on the bottom then, right? Move this 6 tile up. Then it's just going to keep stacking these actions one on top of another until it gets to that final goal or outcome. Now, a heuristic strategy is a method for making decisions that's a little bit more intelligent and it uses a little bit more knowledge than just a full-on brute force, which is what we just looked at in the search tree. It tried every single example until it found it. So requirements for it to be a good heuristic strategy are things such as it has to be easier to compute than a complete solution. So if doing brute force is the same as heuristic, then why bother? So it must provide a reasonable estimate of proximity to a goal. You have to be able to somehow do a measure of how close you are to that goal. Here's our example of a heuristic strategy for our tile puzzle. Okay, so we've got 3 tiles that are 1 position away, and we've got 2 tiles that are 2 positions away. So if we say we've got 3 plus 2, that gives us 5 tiles. Let's use how many tiles are not in the correct spot as our measurement. So this next slide, I'm going to preface this. Do not get in the weeds. I promise you, I'm only going to put it up here for a short amount of time because I don't want you copying this down. But this is what we can kind of look at as pseudocode for an algorithm that's going to look at that heuristic. We're going to establish a start position, and then while we keep going, okay, while we're in a loop, the instructions for heuristic are we're going to select the leftmost leaf with the smallest heuristic value. Now, for our example, we said that the number of tiles that are not in the correct position is our heuristic value, okay? Then it's going to do a new calculation and calculate a new heuristic, and then it's going to record that heuristic, and then it's going to basically do that over and over again. Finally, it's going to get to a point where it finds the goal, and that is going to be the answer, and it's going to backtrack and do all of the moves in order to get it to that goal. Okay, that's going away. We're not going to be able to see it again. So let's apply that, though, to our 8 tile puzzle. So here I've got the jumbled at the very, very top. So first, this is going to be our initial state. or the root state of the value. Now remember, we said it's 5 because we said there are 5 tiles not in the correct location. So we're going to use the heuristic value as 5. When we look at this, there are only 3 possibilities that we can do. We can move the 5 down, the 6 up, or the 2 over, right? Because that's where our empty space is. So that's where our 3 children come from off of this, okay? Then off of that new configuration, we're going to find out what that heuristic value is, okay? So now in this first one, 6 is in the correct position, so we're down to 4. In the middle value, well, nobody's in the right spot. So we actually added 1 worse. And then all the way on the right over here, when we move 5 down, you know, we're a little bit closer and it's a 4. Now, what are we going to do with the next step? So remember, we're going to go leftmost lowest number. So we've got 2 4s as the lowest number. We're going to pick the leftmost one to basically move on with. So we're going to select that first one. Now with that first one, we have 1 empty spot with only 2 moves because it's a corner. The 6 can go down, but then that puts us right where we started. So that's not an option. Or the 8 can go over. So of course we're going to take the 8 moving over. That again, we calculate our heuristic value, and we went from 4 to 5 because 8's no longer in the correct location. So now we look at the 3 leaf nodes here, which is now the 5, the 6, and the 4, to make a decision as to which to choose next. So remember, lowest number. So 5, 6, and 4. We're going to choose the 4. So let's see what that looks like when we choose this 4. Okay, so 4, what we have is another corner. We only have 2 options to move the 3 or move the 5. Again, we're not moving the 5 because that puts us back at the beginning. So let's move the 3. So we move the 3 over, and now look at that. Now we actually have another number in the correct location. So our number goes down to 3. And again, we look at the lowest number, so the 3. So let's keep working with that 3. Well, if we do this and we keep moving on, you can see here the ending result that we're going to get. Now remember, you're going to go number first and then leftmost first. It's going to look very similar to that search tree that we had, but it's going to be a little bit smarter than that search tree that we had. So we're not exhausting and doing every single one. We're being a little bit more smart about what we're choosing. So now, you know, even though we took a wrong turn at the beginning here, we went all the way to the left, it put us right back on track and brought us back over to the right after that 1 step. So we only wasted 1 step, not a whole bunch of steps like we would have wasted in a search tree. So you can see how it's a little bit smarter of a version of a search tree than, you know, what we saw before. Now, additional areas of research, you know, there are a lot of tasks that humans do that are quite difficult for a computer or a machine to mimic. So researchers definitely try to isolate what some of these you know, tasks are, and to find solutions in these areas by trying to either apply shortcuts or limiting the scope of the problem. But remember, we are trying to mimic the human brain, the human body with machines. So that's, you really have to make sure that you're looking at it in that respect when you want to kind of go further with artificial intelligence. Now, handling real-world knowledge is an issue. So real-world knowledge is basically anything that's being retained by the human mind. It may not be on paper. It may be experience. It might be something passed down through generations, right? It's not just the, you know, representing the storage and the way to represent these models and this information. It has to be readily accessible, and sometimes getting that accessibility is an issue, right? So another approach to developing better knowledge extraction systems has been to get various forms of reasoning into that process. Okay, we call that meta reasoning. Okay, same thing as metadata, is data about data. Meta reasoning is the reasoning behind why we reason things the way we do. To me, it just sounds like a black hole a little bit. That's why AI is not in my wheelhouse. But an example can be used in like context of database searches. We can apply actually closed world assumptions, and that's how we're going to assume something is false until it is actually proven true. Okay, this can limit some of that expansion that is out there with the data that we have. Finally, we have a problem called the frame problem, and that is keeping that stored knowledge up to date as possible. If an intelligent machine is going to use knowledge to determine behavior, then the knowledge has got to be as current as possible. Otherwise, the behaviors are not going to actually mimic what a human does. The next level we can look at is called supervised training. Typically, a human will create a training set. The training set is a full set of input, processes, and output. And the machine will take that training set and find common characteristics and kind of find patterns within that training set that it then can apply to the rest of the data set. This is good at distinguishing people's handwriting or voice, determining whether it's a spam email or junk email versus a regular email, and things of that nature. The third level is by learning by reinforcement. So learning by reinforcement, it gives a general rule to the machine in order to judge for itself when it has succeeded or failed. So it's really good for playing games like chess or checkers. There's definitely a definitive you've won, you've lost. And learning by reinforcement allows the agent to act on its own as it learns to improve its behavior over time. So it is really just doing self-checks to see if this is the correct way to go, if it was not, and keeping data on that. So sometimes there's a group called unsupervised training in this reinforcement realm, and it's going to have different goals. This would be clustering algorithms and component analysis. And several different ways that we can use this would be to infer different patterns or meanings from data. And again, remember, this one has the most minimal human interaction with it. Now, genetic algorithms is a strategy for discovering the answers over time. Okay, so it's an evolutionary process, which is why we kind of go genetic. Okay, so it's going to begin by generating a random pool of trial solutions. So each solution is going to be a guess. Okay, so say in the case of our 8-tile puzzle, it can just be a random sequence of tile movements. Each solution that you've come up with is called a chromosome, and each component is called a gene. Okay, we just basically mimicked what we do in biology. Since each initial chromosome is random guess, it's probably more unlikely than likely that it will represent the solution to the problem. So the genetic algorithm needs to generate new pools of data where each chromosome is an offspring of 2 parents, okay? So you're combining the random pools in different ways. So the parents are going to be randomly selected from the previous pool, and the parents are then going to be run through the system in order to give what the answer would be, and that is the child chromosome. So this is going to determine which chromosomes or decision solutions are best to be taken. A probabilistic preference is used to select the parents. Each offspring is a combination of the parents' genes. So, unfortunately, there's no assurance that the genetic algorithm will ultimately find a solution, but research has actually demonstrated that it can be effective for solving a surprisingly wide range of complex problems. So taking a quick look at like a biology, 101 from way back in middle school, artificial neural networks that are going to provide a computer processing model that mimics the networks of the neurons living in a human's biology system. A biological neuron is a single cell with input tentacles and an output tentacle. So they have names, they're right there. The signals are then transmitted through the cell's axon, and it's basically going to understand what to do. Okay, so each input is multiplied by a weighting factor. The output is going to be 1, and this, they kind of use those logic gates that we talked about. So the output is 1 if the sum of the weighted inputs exceeds the threshold value, or it's going to be 0. So it kind of drills down everything coming from all those other inputs as a 1 or a 0. The network is programmed by adjusting those weights using feedback from examples. So again, we're having that repetitiveness that's coming around. And we are learning from that repetitiveness. Now here, this is within a processing unit. This would be a single neuron. I do not get too far into the weeds with these. There was a lot of math kind of things going on in here. Really, all you want to see from this is that there is an effective input that has weights based on each one of the various numbers of inputs there. And then it's going to compare the effective input to some value. And then it's going to say, do I keep going or do I stop? That's the 1 or the 0. That's really all that happens. But there is an example, there we go. Okay, so this is kind of representation with a neuron. And in this exact figure, we've got a threshold of 1.5. Say we've got weighting factors on the -2, the 3, and the -1. We compare that to that 1.5 and see if we keep going or whether we stop. Again, don't get too far in the weeds. This is getting into some really heavy stuff. This is going to be the last slide I show on the heavy stuff, and the next we're going to go on to a little bit more fun stuff. But this could be the input and the output with 2 different programs. You can see that you end up with the same output. So finding what is in that center, you know, especially when we talk about the abstraction of it, it doesn't matter. It's hidden from the user. All the user wants to know is if they put a 1 in a 1, we're going to get a 0.5 out. So we want to make sure that our output is going to be correct, but there are various ways of getting there. And that's really the main idea of this slide. Okay. 2 more slides and then we're done, I promise. Robotics. Robotics are truly autonomous robots that require progress in perception and reasoning. So it is going to take anything that it has and the results of it and learn from it. It uses it as new knowledge. There are major advances being done in mobility and the way that robots can move. We can plan development versus reactive processes. So are we going to anticipate that a wall is there, or are we going to wait till we bump into the wall to see what we do? And, you know, one of the newer topics is evolutionary robotics and how things progress as different things change. And again, we're almost done. Last slide, I promise. Considering the consequences. So this is where that blurry line comes in of artificial intelligence and when is too much too much. So when should a computer's decision be trusted over a human's? Human intuition is something that's always going to be there, and there really we haven't figured a way how to mimic that. If a computer can do a job better than a human, why should a human do the job anyway? There is, again, something, you know, behind the human element. You know, we have replaced humans when it comes to things that are dangerous or, you know, that a human should not be doing. But if we're going to automate everyone's job, then what's the purpose in having jobs, right? I mean, I'm okay with that. And finally, what would the social impact if computer intelligence surpasses that of many humans? I'd love to hear the answer of these questions, and what other questions do you have when it comes to the consequences of artificial intelligence? Well, this concludes my lecture for chapter 11. Again, only one more section to go and we are done. As always, I'm available through email or voicemail if you need to talk. Any questions, just let me know. Bye.